So let's turn to the topic of Locke on measurement. What do these Lockean metaphors have in common? All that can fall within the compass of human understanding. Essay 4, 21.1. 'Tis of great use to the sailor to know the length of his line, though he cannot with it fathom all the depths of the ocean. 'Tis well he knows that it is long enough to reach the bottom at such places as are necessary to direct his voyage. Our business here is not to know all things, but those which concern our conduct. If we can find out the measures whereby a rational creature, put in that state which man is in this world, may and ought to govern his opinions and actions depending thereon, we need not be troubled that some other things escape our knowledge. Well, of course, the answer is that they all have to do with measurement. They both have to do with measurement. Indeed, Locke uses the term measure in 14 of the section headings in the essay concerning human understanding, and the term measure or measurement occurs 156 times in the essay. If we are to get the measure of Locke as a philosopher, we have to deal with the place of measurement in his thought. Not simply his profound interest in metrology, but the central place of measurement in his conception of how we acquire knowledge of the natural world. Locke was one of the first English philosophers to write about what we now call a philosophy of measurement. Drafts A and B of an essay concerning human understanding, which were written in 1671, and the essay itself, first published in 1690, sketch a form of realism about number and measurement. Furthermore, for Locke, measurement plays an important role in his conception of how we acquire knowledge of nature. A central thesis in Locke's theory of knowledge acquisition is that our knowledge of nature is seriously constrained by two measurement problems. First, there's the problem of measuring the submicroscopic, that is, the determination of measurable quantities that are too small to be perceived, even with the assistance of instruments like microscopes. And second, and even more pressing, there's the problem of the standardization of current measures. These are the three salient issues pertaining to measurement in Locke's philosophy. The metaphysics of measurement, Locke opts for realism, or so I claim. The problem of the determination of unperceived quantities, and the problem of standardization of current measures. I've tried to address the first two issues in my book on Locke and natural philosophy, and today I should like to focus on the third problem, the standardization of measures. One thing is for sure, and that is, of the three issues, the issue of standardization of measures is the most historically interesting. And this is because Locke came up with three separate proposals for standardization of measures that he hoped would be adopted by the Republic of Letters, or even better, by the government of his day. The proposals were first for a standard of length, second, a recommendation against the devaluation of the English silver coin, and third, a proposal for calendar reform. As things transpired, only the second of these proposals was adopted, and in this Locke seems only to have played a minor role. In this lecture, I want to examine the history of Locke's proposal for a standard unit of length, and in doing so I will weave into the story Locke's philosophical reflections and the philosophical motivations that drove this issue in Locke's thought. Time doesn't permit parallel treatments of Locke's other proposals, yet there's a sense in which they're motivated by the same set of philosophical considerations, and thus not too much is left out if we focus solely on the standardization of length. So let's look at Locke's early interest in standards of measure. By the mid-17th century, experiment had come to play a central role in the practice of natural philosophy. So important was it that a new natural philosophical methodology emerged in England in the 1660s called the experimental philosophy. And it goes without saying that the primacy of observation and experiment in natural philosophy brought the problem of the standardisation of measures to the fore. Quantities such as weight, length, time and temperature were in desperate need of universal standards of measure. Furthermore, recent developments in natural philosophy had given rise to the need for measures of newly discovered qualities, such as the spring or pressure of the air, but also the need for the determination of constants, such as the speed of sound and light, and the need for accurate determinations of location and elevation. In short, in the second half of the 17th century, metrology obtained an importance that it had never before experienced. To be sure, metrology had always been an essential feature of astronomy, but even that science was caught up in the new push for exactitude in the multiplication of observational data. It was not long before there was an institutional response to these issues. The standardisation of length was the most pressing problem, and it was addressed by the Royal Society of London as early as 1661. Now remember, the Society was founded in 1660, so it was really one of the first things they addressed. Christopher Wren recommended that the length of the seconds pendulum be taken as a universal standard of length, a recommendation that met with widespread approval. A committee was formed and various issues relating to the proposal were discussed, such as decimalisation of the subunits of length, the relation to current and local international standards of length, and so on. And an important treatment of these issues soon appeared in John Wilkins' An Essay Toward a Real Character and a Philosophical Language of 1668. Locke began to reflect on these problems of measurement as early as 1671 in the first drafts of the essay. He mentions the seconds pendulum a number of times in draft B in the context of an extended discussion of the measurement of time, a discussion that formed the basis of the chapter entitled Duration and its Simple Modes in the first edition of the essay. Locke's initial concern in this part of draft B is with time as a simple idea. According to Locke, the origin of our idea of duration is our experience of the succession of ideas in the understanding. He claims that the idea of time seems to me to be nothing else but the considering or assigning the length or distance of duration between any two assigned instants wherein any two things did or might exist by some common known measure. As a result, the idea of duration emerges as the central notion. Locke says, time, therefore, to duration is as place to extension, which is nothing but examining or assigning the distance of any 2 points by some common known measure. Well, what is the standard measure for duration? Locke claims that the ideas in a waking person in a constant, regular pace continually succeed one another, which succession of their ideas is, as it were, the measure and standard of all other successions. The problem is, however, unlike standards of measure for extension, in the case of duration, it's impossible to establish a lasting standard and keep it by us, but only in our memories, whereby to adjust other measures of duration. For the parts of duration being perpetually fleeting and in constant succession one to another, so that it is impossible ever to bring two of them together to examine their equality or inequality, we are left only to guess. And thus we resort to measures based on periodical motions. Though the periodical motions of the sun or moon have been by the greatest part of mankind made use of for the common measures of duration, and of late the motions of a pendulum, and so time thought to be the measure only of motion, yet it is a mistake to think there can be no duration or time where there is no motion, though generally motion hath been made use of for the common measure of it. There are two problems with this practice according to Locke. The first pertains to the theory of ideas. Our idea of duration does not presuppose the idea of motion, but is independent of it. The second problem pertains to the measures themselves. We are mistaken if we presume that the periodical motions, such as the annual and diurnal revolutions of the Earth, are equal. Just as we cannot know the equality of the duration of two successive ideas, we cannot know that two successive periodical motions are exactly equal. Nor can we be certain that any two successive diagrams of the same pendulum are exactly so, because we can never put them together to measure them. We cannot be sure that the cause of that motion which we know not shall always operate equally, and that the medium in which the pendulum moves is not constantly the same, either of which varying may alter the equality of such periods, and thereby destroy the certainty and exactness of our measure by motion. This latter point, namely that there might be variation in the periods of a pendulum, will prove important because it bears on later claims that Locke will make concerning his proposed standard of the measure of length. Incidentally, in this discussion of the measurement of duration in Draft B, Locke also provides an early statement of the problem of circularity of coordination in the philosophy of measurement. If the measure I stand to be the diagrams of a pendulum as the certainest and equalist of all, I ask again, how can I know their equality? If I say because I find them always correspond with the motion of the sun, that's to make the motion of the sun the standard which before we were in doubt of, and so prove in a circle, i.e. the periodical motions of the sun are exactly the same, of the same duration, because they keep pace with the periodical motions of a pendulum. And each diagram of the same pendulum is of the same duration with those before and after, because I find them to correspond with the periodical motions of the sun. The problem of circularity. Meanwhile, as Locke was brooding over these problems in measurement, Christian Huygens set about sorting out the physics of pendulum motion and the design for the construction of a pendulum clock, which in turn enabled the determination of the length of a second's pendulum. And his results were published in 1673 in his Horologium Oscillatorium. And there's the title page. And here is how Huygens put the issue. 1673. For the case in which each oscillation of the pendulum marks off 1 second, divide this distance into 3 parts. Each of these is the length of an hour foot. By doing all this, the hour foot can be established not only in all nations, but also can be re-established for ages to come. Also, all other measurements of a foot can be expressed once and for all by their proportion to the hour foot, and can thus be known with certainty for posterity. For example, the Parisian foot is related to the hour foot as 864 to 881. In other words, if the Parisian foot is given, then we would say that a simple pendulum whose oscillations mark off seconds of an hour has a length equal to 3 of these feet plus 8 1/2 lines, which is a division of a foot. So that's Huygens' ambitious claim. The claim that the hour foot can be established not only in all nations, but also re-established for ages to come. This claim was immediately challenged by observations of made by Jean Richet near the equator at Cayenne. But this is to get ahead of our story, and we'll return to that in a while. Let's move now to Locke's travels in France. Locke left for France on the 12th of November 1675, where he remained for 3.5 years. His first extended stay was at Montpellier, where he took notes on the local weights and measures, comparing them to English measures. In fact, notes on French provincial and classical weights and measures are scattered throughout the journal in the early months of the trip. On the 27th of May, 1676, he made a journal entry on the seconds pendulum derived from the Journal des Savants. And while staying in Paris in August 1677, he read a review of Huygens' Horologium in the Journal des Savants and noted the following in his journal on the 6th of August. The length of a seconds pendulum according to Mr. Huygens' computation being 888 demi-lines, or which is the same 3 foot 8.5 lines of the foot of Paris. The very next day, he noted down the French units of length and their relation to each other and proposed a unit of measure, which he called the graille. It was 1,000th part of a philosophical foot. A philosophical foot is 1/3 of the length of a seconds pendulum in Paris, as determined by Huygens. it was equivalent to Huygens' hour foot. As for comparative measures, the Paris foot was equivalent to 981 gris, less a third of a gris. Thus, Locke's gris was based upon the length of Huygens' seconds pendulum, as reported in the Horologium. Locke's name, the philosophical foot, for 1/3 of the length of the seconds pendulum, probably derived from John Wilkins in the book which I mentioned earlier, who uses the term philosophical foot. 2.5 months later, Locke took receipt of his own brass ruler made according to the philosophical foot. In fact, the instrument was a sector or compass of proportion, and there is a sector that dates from about 1630, so some 45 years before Locke had his made up. But Locke's would have been a very similar design to this. And he had it marked, and he records in his journal the markings. So he had the universal foot, the Parisian foot, D was marked on it for Denmark, L for Leiden, E for England, and PR for the Palma Roma. The fact that his marks include Denmark suggests that Locke was in dialogue at this point with the Danish astronomer Ole Rømer on questions of metrology. Rømer resided in Paris, having been brought there in 1672 by the leading French astronomer Jean Picard. Locke returned to his unit of measure again on the 29th of January 1678, while still in Paris. He now worked out how many gris make up the different feet that he'd marked on his ruler. But more importantly, he spells out the decimal subdivisions of the philosophical foot and compares the gris to the English inch. And this is another journal entry. A pendulum of seconds being divided into 3 equal parts, each of them makes that which may be called the philosophical or universal foot, the 10th part of which foot I call an inch, the 10th part of that inch a line, the 10th part of a line a gris, so that the English foot is 9 inches, 2 lines, 0 gris of the philosophical foot, and consequently the English inch is 7 lines and 6 2/3 gris, and that's the definition of the gris. On the 2nd of July 1678, so not too long after, Locke packed away his brass ruler, along with other things, including a manuscript entitled Essay de Intellectu, that is, a draft of the essay, and set off on another trip around France. On returning to Paris, he continued to make observations concerning the Paris foot, and in early March 1679 he compared it with the English foot in the company of the astronomer Adrien Auzout. Then on the 17th of March 1679 he visited the home of Picard, who checked the calibration of Locke's own ruler. I examined my universal foot, on which is the compass of proportion, at Mr. Abbé Picard's, and he found it just. He also told me that a pendulum of seconds contained of our English measure 39 1/8 inches, of the Paris measure 36 pouces, 8.5 lines, or 36 708,000 pouces. The foot of Paris being divided into 1,440, i.e. tenths of a line, the English foot contains of them 1,351. Locke also recorded some advice from Picard on the mounting of and the calibration of pendulum clocks. Locke then left for England 6 weeks later on the 30th of April 1679, so came the end of his long sojourn in France. When he left the shores of France, he was accompanied by Ole Rømer, who had been charged by the Académie des Sciences with the task of determining the precise length of the seconds pendulum in London and the relative length of the English foot. Incidentally, Rømer would return via Paris to his native Denmark just 4 years later in 1683 and oversee there the introduction of a new system of weights and measures. And in 1699 he would reform the Danish calendar. The new Danish standard of length adopted in 1683 was based on the seconds pendulum. 10 days after returning to England, Locke received a letter from his Parisian friend Nicolas Toinard that contained what might have been slightly unsettling news. Toinard writes, Monsieur Richer, who paid me the honour of coming to me recently, persisted in saying that the seconds pendulum is shorter by a line and a quarter at Cayenne than at Paris, to which I objected to him that Monsieur Picard had not found any difference in 5 stations from Copenhagen to Montpellier. Cayenne, however, is 4 degrees 56 minutes north and 3 hours 28 minutes to the west of the observatory in Paris, which is latitude 52 degrees. If Richet's measurements were correct, then the prospects of using the philosophical foot as a universal standard of length would be scuppered. Locke initially, at least, seems to have been nonplussed. He wrote to Boyle a month later, on the 16th of June 1679, concerning a case of unusually long fingernails and toenails on a boy whom he saw in Paris. The longest of all, he says to Boyle, was that on the middle finger of the right hand, which was 3 inches and 9 gries long. Realising that he ought to explain his unit of measure, he concludes as follows. Before I conclude, I must not forget to tell you that the measure I made use of was the philosophical foot, i.e. 1/3 of a pendulum of seconds, which I divided thus: the foot into 10 inches, the inch into 10 lines, the line into 10 gries, so that a grie is 1,000th of a philosophical foot, which measure, whatever it be for other purposes, I thought the fittest for philosophical communications, and therefore made use of it in this and several other occasions. But I have troubled you too long already to mention here the conveniencies of this foot, and, as I think, of the way of dividing it by decimals. Clearly, Locke still had confidence in his philosophical foot and its 1,000 gries. Meanwhile, Römer had determined the relative measure of the philosophical foot and related this finding to Locke, who recorded on the 21st of May, Römer tells me that our English foot is 1 to 920 gries of the universal foot. And of course, Römer was taking this back to the Academy in Paris to confirm his findings with them. And this confirmed the comparison that Locke had made the previous year in Paris. So we've looked at Locke's early concern with measurement in drafts A and B. We've then turned to Locke's travels in France, and we've seen an enormous amount of interest on Locke's part in the standardisation of the measure for length. And we now are going to make a little bit of an excursus and look at Locke and the question of longitude. One reason for continued confidence in his standard of measure was the steady stream of important results issuing from the work of Picard. Picard had been set the task of revising the map of France, and to do so he needed accurate measures of longitude. And this was achieved by setting 2 pendulum clocks at different locations and recording the time of the phases of the first moon of Jupiter. There we have the phases, and it was recorded when the moon was 1 diameter from Jupiter, then adjacent to Jupiter, and then when it disappeared. So you've got 3 readings, a very, very accurate way of doing it. That technique was devised by Cassini. At those locations on the same day, so that there had to be one in Paris and one at this other city where the longitude was being determined. They need to be done with calibrated pendulum clocks. On the 20th of September 1679, so right near the equinox, Toinard wrote to Locke with the results of Picard and Römer's latest determination of the longitude of Brest, the most westerly town on the French Atlantic coast. They found a difference of 27 minutes and 31 seconds between Brest and Paris, and this was duly reported to Locke by Toinard. This figure differed from the most recent map of France by 5 minutes and 9 seconds. That's rather a lot, which meant that a significant revision of existing maps was required, as Toinard points out to Locke. And here we have an image where you can see Brest on the old map was here, and the revised map of Picard is moved 5 degrees to the east. It was this sort of detail that fascinated Locke, and which he went out of his way to collect. Throughout his journal, for instance, there are entries for longitude for various towns in France. But the salient point is, of course, that none of this work could be done if the pendulum was not a reliable timekeeper. and given that Brest and Paris were at slightly different latitudes, there might be cause for error should Richet's findings at Cayenne be verified. An indicator of the extent to which Locke followed the details of Picard's findings is found in his attitude to one of Picard's most important publications, the Connaissance des Temps. It's a kind of French ephemerides that supplied all sorts of useful data, including advice on the use of pendulums. This publication first appeared in 1679, and Locke procured a copy. He was keen to get the second issue and wrote to Toinard concerning it. Seeing that the pamphlet entitled La Connaissance du Temps is so useful, I wonder why we are given no hope of having it beyond this year. But that is how mankind is usually treated. The more useful anything new is, the more difficult it is to make it available. Don't often hear Locke whinging, but there he is having a bit of a whinge to Toinard back in Paris. In the event, Locke did procure the second issue as well as two others. So it's worth turning to the first two issues to see what they have to say about the longitude of Brest. In the 1679 issue, we find that Brest has longitude of 0 hours, 22 minutes west of Paris, and it's the top line on the image here. So we have latitude and longitude 022. That's in 1679. The 1680 issue, which is alongside it on the slide, has the revised figure of 0 hours and 28 minutes, reflecting the new finding of Picard and Römer. It's unlikely that this point was lost on Locke, because he had a keen interest in what had come to be called special geography. In fact, it's most likely that it was around this time that Locke procured one of his two copies of Newton's edition of Varenius's Geographia Generale, which was published in Cambridge in 1681. That's the original Varenius title page, and that's the Newton edition of second edition of Varenius of 1681. The first was 1672. Newton's Varenius is an understudied work that bears on our story in some important ways. Locke had two copies of the second 1681 edition, and one can only surmise that he bought the first around the time of publication and received the second copy as a gift from the editor, Newton himself, after they met on or before February 1690. Like Locke, Newton was fascinated by the new developments in special geography. Unlike Locke, he probably taught geography at Cambridge. It was included in the statutes for the Lucasian Chair of Mathematics and was taught by his predecessor Isaac Barrow. Also, unlike Locke, he had the requisite skills to make a contribution to the field. It's most interesting, therefore, to compare the first 1672 edition of his Varenius with the second 1681 edition, the one that Locke owned. In the section on the discovery of longitude in the first edition, there's no mention of the use of pendulum clocks or the timing of the phases of the moons of Jupiter. By the second edition, all of this had changed. Newton had assimilated the new French techniques and discoveries and apparently had used them to improve on and update the table of determinate longitudes and latitudes that was originally included by Varenius himself. Thus, the second edition of Newton's Varenius includes two new sections outlining new methods for determining longitude. The first is the modus quintus per planetas jovialis, the fifth mode, finding longitude by the planets or by the moons of Jupiter, and the second, the modus sextus per horologium automaton, sixth mode by the automated pendulum, or the pendulum clock. Neither of these methods was present in the first Cambridge edition. Incidentally, this textual material, buried as it is in Varenius's book, is authored solely by Newton and comprises a minor, though important part of the background to the writing of the Principia, background that was missed by Heriville and, as far as I can determine, by most subsequent Newton scholars, if not all. This, then, is part of the backstory of how Newton came to appreciate the significance of Richet's and Véran and Desaix's claims about the variation of the second's pendulum close to the equator in the first edition of the Principia. By the early 1680s, Newton was fully apprised of these developments in special geography and soon came to see their implications for his account of the shape of the Earth and the nature of terrestrial gravity. Though it must be admitted that the two editions of Newton's Varenius remain Cartesian works predicated on a spherical Earth and set in a Cartesian vortex theory. Of course, the third Cambridge edition of Varenius, edited by James Durin, published in 1712, the year before the second edition of Newton's Principia, overthrew all the Cartesian vortex theory and everything, and gave a kind of Newtonian spin on Varenius' special geography. But that's another story for another day. Turning to Locke. Locke's interest in Varenius was almost certainly inspired more than by parallels between Newton's later edition and the work of Picard. For Varenius's book, which is cited 3 times in Boyle's Spring of the Air, and while it doesn't style itself as a Baconian natural history, its survey of special geography is almost a perfect match with Boyle's General Heads for a Natural History of a Country, Great or Small, published in the Field Trans in 1666. And in particular, both Boyle and Varenius were concerned with the nature of the air and its variations, such as different types of winds, where they came from and what their impact was, and so on. And in fact, the project of special geography in England was sometimes styled as the project of natural history. So Varenius introduced the term special geography, and there are works on special geography, but it's picked up in the second half of the 17th century in England in translations and discussions, and often called natural history. Thus, there's a broader methodological framework to which Newton was committed and to which he made a modest Locke was committed and to which he made a modest contribution that was continuous with much of the content of Newton's Varenius and Picard's Connaissance des Temps. We need to return, however, to 1679, before the appearance of the second edition of Newton's Varenius, for at some point toward the end of that year, that's the year Locke returned to London from France, he may have had his first misgivings about the reliability of his standard of length. He asked Römer his view of the matter, and Römer replied from Paris, where he had returned after his trip across the Channel with Locke. As to the question you ask me about the pendulum, I have not yet wholly satisfied myself, let alone you, as to what the right answer is. It's certain that, at any rate, that it's insensibly longer in your country by, I think, a 6th or a 7th part of a line, assuming that the uncertainty of the universal foot resulting from these experiments doesn't exceed the 20th part of a line. Nevertheless, Locke persevered with his standard unit of length, and we find him using it again the following May when reporting to Toinard on some massive hailstones that had fallen in London, one of which was 420 gris in circumference. He also used the gris to establish the precise dimensions of a document cabinet that he designed, a prototype of which he showed to Römer while he was with him in London. It was a 10 by 10 set of pigeonholes, and it sparked the interest of Toinard, to whom Locke sent the exact dimensions, again in terms of the gris. What then about Locke's essay and the standard of length? It would take at least another 8 years before Locke again thought seriously about the gris, or until we have any more evidence, at least, that he'd been thinking seriously about the gris. While he was in exile in the Netherlands in 1688, he reviewed a very technical work in natural philosophy in the Bibliothèque Universelle, perhaps at the behest of the editor of the journal, his friend Jean Leclerc. The book was none other than Isaac Newton's Principia Mathematica, which had been published in Latin in 1687. In his summary of Book 3 of the Principia, Locke relates the following claim of Newton. The Earth is 85,200 Paris feet, or 17 miles higher at the equator than at the poles. For otherwise the sea would engorge from the poles to the equator, inundating the whole surface of the globe. The force which proceeds from the diurnal motion and away from the centre of the parts of the Earth at the equator is in relation to its gravity as 1 to 290 over and 4/5. The shape of the other planets is somewhat close to that of the Earth. In other words, the Earth's an oblate spheroid, and so are the other planets. The gravity at the pole is to the gravity at the equator as 692 to 689. Hence it is that the review says here in French longitude, but we'll see that that can't be right. Hence it is that the longitude found by the method of the pendulum, which makes its vibrations at each second at Paris, latitude 48.45, is 3 feet and 17/24 inches, and surpasses the longitudes found in the Isle of Gorée at latitude 14.15 by 81/1000, at Cayenne in Guinea, which is at latitude 5 by 89/1000, and at the equator by 90/1000 inches. So this is Locke's review of Newton's Principia, summarising content that he found interesting in book 3 of that book. This is what Locke picked out. Not much else. The second paragraph here is somewhat garbled. Newton, and therefore we take it Locke, was not speaking about longitude in this context. Rather, the point at issue is the length of the seconds pendulum. So it should be length, not longitude. It's as if Locke had written the review in Latin and Leclerc had not understood it correctly as he translated it into French. Be that as it may, Locke could hardly have missed the import of Newton's claims. Newton, in his most impressive book, had taken Richet's observations and the later observations of Varane and Deshaies on the Isle of Gorée in 1682, he'd taken them seriously, and he'd clearly seen the implications for his view of the shape of the Earth and the variation between the gravity at the equator and at the poles. If Newton was correct, it would imply that Locke's Graph is not a universal measure, because the length of the pendulum will vary with latitude. If he had earlier sided with Thoinard and Picard against Richet, Newton's treatment of the subject forced a rethink. All of this happened as Locke was writing book 4 of the essay. It's of singular importance, therefore, that Locke added a crucial qualification to his description of the Graph when he refers to it in book 4. A Graph is 1/10 of a line. A line, 1/10 of an inch. An inch, 1/10 of a philosophical foot. A philosophical foot, 1/3 of a pendulum whose diagrams in the latitude of 45 degrees are each equal to 1 second of time, or 1/60th of a minute. I have effectively made use of this measure here. This is chapter 10 of book 4 in the essay, and the parts of it under a decimal division with names to them, because I think it would be of general convenience that this should be the common measure in the Commonwealth of Letters. The qualification, of course, is in the latitude of 45 degrees. This didn't appear in the definition that Locke gave Boyle in 1679. This didn't appear in the initial definition in Locke's journal. So what are its implications? Well, first, it's almost certain, coming as it did around the time that Locke wrote the Principia Review, that he'd seen the implications of Newton's claims and therefore Richet's observations. The philosophical foot will vary with latitude, and Locke's own ruler is not based on a universal standard. Second, there's the question of why Locke chose latitude 45 degrees for the standard. In this, he wasn't alone, and it was a natural choice given that it's the midpoint between the equator and the poles. Though it was, for an Englishman, highly impractical, for no part of England crosses the 45th parallel. If one were to calibrate a seconds pendulum and then determine the length of the philosophical foot and Graph, one would have to go to the continent. Having said this, it's worth noting that exactly 100 years later, after the publication of the essay, the first proposal in revolutionary France for a new system of weights and measures advocated using a seconds pendulum calibrated at latitude 45 degrees. And this was recommended to the English Parliament. The French didn't adopt it, and the English flirted with it for a while, but eventually didn't take it up. Third, and perhaps more disconcerting, are the implications for Locke himself. For what we know about his ruler is that it was made and checked in Paris and not at the 45th parallel at all. Nor does the 45th parallel pass through the Netherlands, so it seems unlikely that Locke had a new ruler constructed in the last years of his exile there. Well, what then does Locke have to say about the seconds pendulum in the essay? In the chapter of duration and simple modes, Locke's really quite sceptical about the accuracy of the seconds pendulum as a measure of a unit of time. Duration in itself is to be considered as going on in one constant, equal, uniform course. But none of the measures of it, which we make use of, can be known to do so, nor can we be assured that their assigned parts or periods are equal in duration one to another. And though men have of late made use of a pendulum as a more steady and regular motion than that of the sun, or to speak more truly of the earth, yet if anyone should be asked how he certainly knows that the two successive swings of a pendulum are equal, it would be very hard to satisfy him that they are infallibly so. This is because we cannot be sure that the pendulum itself is operating uniformly, or that changes in the medium in which it swings are not affecting it. And this leads Locke to the pessimistic conclusion that all we can do for a measure of time is to take such as have continual successive appearances at seemingly equidistant periods, of which seeming equality we have no other measure but such as the train of our own ideas have lodged in our own memories, with the concurrence of other probable reasons to persuade us of their equality. It appears then that there's a tension here between Locke's comments on the unreliability of the seconds pendulum as a standard of measure of time and his evident enthusiasm for the philosophical foot and gry in his correspondence and journal. Locke did trust the seconds pendulum for setting his standard unit of length. And it's of great interest, therefore, that this last quoted passage is phrased quite differently in draft C, which was written around 1685. There, when contrasting the periods of the sun and the pendulum, Locke wrote, if the periods of the sun and the pendulum do at all disagree, it will not be easy for us to determine which is the true and exact regular motion, that of the sun or the pendulum. And if they do agree, we can but suppose or guess at the equality of the periods of that by which we pretend to measure the other. But though the first way of guessing be by the comparing of the length of each period with our own thoughts, yet of the equality we shall be the more confident if there be concurrence of other probable reasons to persuade us of that equality. And I think those most equal where most reasons do concur to persuade us, as it is in pendulums. Here in draft C, Locke's saying that in the case of pendulums, reasons do concur to persuade us that they're reliable measures of time. It's the concurrence of other probable reasons underlined in the slide. That's the key here. It's the key for establishing that the passage in the essay derives from this passage in draft C. And it's the key because while Locke doesn't elaborate what those other probable reasons are, it's almost certain that they include corroborative calibrations of seconds pendulums in different places and using different celestial phenomena. What we have here then is an adumbration of a solution to the coordination problem. The concurrence of probable reasons provides grounds for trusting the seconds pendulum as a measure of time. Disappointingly, however, Locke did not incorporate this in his essay when it reached its final form. We now turn to the period after 1690, after the first edition of the essay. The trouble didn't stop there. Locke met Newton sometime before mid-February 1690, and they soon struck up a friendship, and in 1691 Newton presented Locke with a corrected copy of his Principia. Ever on the lookout for constants and measures, Locke was struck by Newton's estimate of the speed of sound. In the first edition of the Principia, Newton had set the parameters for the speed of sound somewhere between 920 and 1085 English feet per second. By 1689, he'd revised this to between 984 and 1094 English feet per second. And we know this because it's among the corrections that he gave to Fatio in 1689, which Fatio then passed on to Christian Huygens. And they were published actually in 1701 in a mathematical treatise. Newton kept on experimenting on this problem, and by 1691 he'd revised the upper parameter again. So the second revision was 1094, and the third revision is 1111. And his latest corrections, or latest calculations, were included in the corrected edition that he gave to Locke, and here they are. So this is the 1687 first edition of the Principia, which had 1005. Newton had gone through two sets of experiments, corrected it again, one set, and then he corrected it again, got another set, and this is the third corrected set, and we only have it here in Locke's corrected edition of the Principia, which he gave him in 1691. In subsequent years, Locke noted this estimate in his notebook. It's not just that we didn't just find that here in his annotated edition of the Principia, it's in his notebook. In subsequent years, Locke recorded other natural philosophers' estimates of the speed of sound in the same notebook, in fact on the same page. Locke was clearly aware that the determination of the speed of sound was still an open question. The salient point, however, is that the experiments contrived to determine the speed of sound use pendulums. Locke was fully apprised of this. If Newton was right about the length of the seconds pendulum varying with latitude, then any possible inaccuracies in the measurement of time would ramify through to the measurement of this and other constants. Locke was happy merely to record the latest estimates and leave it at that. And around about the same time, he made another entry in MS Locke D9 under the heading Pendulum, summarising Newton's claims in the Principia about the different lengths of the seconds pendulum at Cayenne and the Isle of Goree. This was the very point that he'd earlier summarised in the original Principia review of 1688. So Locke's clearly still thinking about variation of the seconds pendulum. So this brings us to the next episode in our story. In 1697, Locke published an account of one who had horny excrescences, or extraordinary large nails on his fingers and toes. Appeared in the Philosophical Transactions. And in this, as we have seen, he measured the horny excrescences by using the Gry. His definition of the Gry here is similar to that which he sent to Boyle in 1679, and not the more qualified one found in the essay. Moreover, Locke's measures of the horny excrescences were identical to those in his journal of May 1678. Thus, he was not using a unit of length determined at latitude 45 degrees, and he was not using a revised philosophical foot. Not quite sure why they've not appeared, but you should see an image of the horny excrescences there. Finally, to bring this very long story to a close, Locke wrote to Toinard on the 25th of March 1698, and this time it was he who raises the question of pendulum calibration in Cayenne. I've read through with pleasure your friend's account of his journey to Cayenne, and I would ask him many questions if I were present, especially about the Isle of Cayenne, where he stayed a very long time. For example, whether they have observed the length of the pendulum in that island, which is so near the equinoctial line. Does this imply that Locke was still not convinced by Réchier's observations? We cannot be sure, and sadly this is where the trail of evidence for Locke's views on the Gry and the philosophical foot come to an end. Well, what are we to make of all this? Locke rubbed shoulders with the leading innovators in metrology of his day: Picard, Römer, Huygens, and even Cassini. He saw and responded to the problem of standardization of measures. He saw and reflected on the problem of the circularity of coordination. He even appears to have glimpsed the solution of epistemic iteration in his conception of the concurrence of probable reasons in relation to the accuracy of the seconds pendulum. Yet, Locke lived in a time of metrological transition. Nothing served to bring this home to him more than his careful reading of Newton's Principia in 1688, where, in the early drafts of his essay, he had spoken freely of gravity as a property of material bodies. After reading the Principia, the term was expunged from the essay. Where he had previously spoken confidently about his own universal standard of measure for length, he is now forced to accept that it was no such thing. I've argued in previous work that our lack of epistemic access to inner corpuscular structure led Locke to what I call an attitude of corpuscular pessimism. Not skepticism, pessimism. A corpuscular pessimism about the prospects for a determinate, demonstrable natural philosophy. I believe that there is strong evidence that on reading Newton's Principia in 1688, his confidence in the prospects of developing a universal standard of length was undermined, and that Locke's corpuscular pessimism was now compounded by a kind of veiled metrical pessimism. His corpuscular pessimism was a long-standing commitment, evident in his early medical essays. His metrical pessimism came rather late, after a long period of firm hopes for the prospects of our gaining a firm grasp on a quantifiable world. For Locke, nature was reluctant to give up her secrets. The standards of measure did not yet fall within the compass of human understanding. Thank you.